We are looking at some continuous distributions and want to look at exponential distribution to start with and gamma distribution. We have actually looked at exponential distribution, haven't we? Or we haven't looked at it?
No, Doc.
Okay, no problem. So we're going to look at the family of exponential distribution. Exponential distributions are subcategories of gamma distributions. And when you look at Poisson, which we have, the time between successive occurrences, the gap between successive events, they have that particular time between successive events in the Poisson have an exponential distribution within it. So there's a connection between exponential distribution and gamma because there is a time between kind of two gamma processes, and that time is exponentially distributed. And just as you normally will have a binomial function, the gamma function will pick the entire gamma distribution, and it will extend the factorials from integers to all positive integers. You can generate the probability density function for the gamma, and you can also generate the cumulative probability density function for that same gamma. So let's look at a random variable that is gamma distributed. It's written as this. A random variable x, which is gamma distributed, okay, this symbol represents gamma. Now, which of you knows this symbol? What's the name of this? Emily, yeah. What's the name?
Doc, I'm not sure.
Emily Yasan.
Doc, I can't see my screen moving on. I don't know. So the symbol you're saying, I can't even identify it.
Emily, did you see the symbol I'm saying?
Yes, Doc.
So how come he can't see? It is the same. Normally when you're writing alpha, beta, gamma, okay, you write alpha. Do you see what I'm writing, Jerry? Do you see what I'm writing,
Yes.
Jerry?
Yes, I can see now.
Okay. And then this is gamma, isn't it?
Yes.
Yes.
Now, this is a small letter for the gamma. The capital letter for the gamma is this one. This one you see there.
Okay.
All right. So that is gamma distributed. Sometimes some people write G, but I like to use the capital gamma for it. So this symbol means that the random variable x is gamma distributed with an alpha parameter, and we talk about this shape parameter, with an alpha parameter called shape, and then with a beta called rate parameter. Okay, so that is a random variable. It simply means that it follows a gamma distribution with the shape of alpha and the rate of beta. Okay, just as if you are talking about normal distribution, okay, we say that a particular random variable is normally distributed with a zero mean and then a constant variance, something like that. Or it's binomially distributed with a 0, 1, sort of. So there are several of these things that you can look at. So that is the distribution of the gamma. Now, this is the gamma function. So if I want to actually indicate a gamma function, I will say that this gamma symbol into bracket alpha, which is a shape, is defined by the definite integral. And this is the definite integral. So this gamma function is the integral of the random variable raised to the power the shape minus the 1. And this is the definite integral is from 0 to positive infinity. Okay, multiplied by the natural log raised to the power negative of the random variable. This is the gamma function, and it is a continuous function. Okay, so any continuous variable x is said to have gamma distribution denoted as this, or denoted as the one that I showed you. And if that is the case, Given this upper value, which is a gamma function, then the probability density function of this random variable x is given by this formula. Now, there are two ways you can write this formula. The first way is this, but the first way is just when x is 0 or positive. Okay. And when x is not 0 or positive, sorry, it's not 0 or positive, when x is positive. Okay. In fact, just a second. I just need to correct that. So you have this function when x is positive, okay, that is the probability density function of the gamma distribution. Or if it is not, then you have a 0. This is another way of writing the function. Now watch it very carefully. You will see that here I have the beta raised to the power alpha. Now in this second one, it was up there. It was down here. And then I bring it up to the upper value. The x is raised to the power alpha minus 1. The natural log is there exactly as it is. But you will notice that here, okay, it is divided by the beta. And that is why when the beta came up, okay, from the bottom, when it came up, it wasn't minus. It wasn't minus because there was another beta out there. So in both cases, the alpha, which is a shape, and the beta, which is the rate of the parameter or the rate parameter, both of them are positive. You can use this one because this is just a set, and you can use that one. This is the gamma distribution function. If you want to find the mean or the expected value of the random variable that is gamma distributed, it is going to be alpha multiplying the beta. It's going to be the shape multiplying the rate. Okay. And if you want the variance, this is it. Please write these two formulas down. Write the mean and the variance of a gamma distributed random variable. Write the mean and then the variance down. Do you remember the Poisson? The mean is lambda and the variance is lambda. Do you remember?
Mm-hmm.
You see, now the distributions are becoming plenty in your head, isn't it?
Yes, Doc.
Don't worry.
Doc, is it alpha beta square or just the beta squared?
Alpha beta square for the variance, right?
Yes.
Yes, for the variance.
So the square is affecting the alpha also?
No, just the beta.
Okay.
So if it was for both, I would have put a bracket there, but it's just for the beta.
Okay.
All right. Now, the gamma distribution, you see, when beta is equal to 1, then the gamma distribution is written like this. And this is called standard gamma distribution, the standard. Okay. Now, you can find the cumulative distribution function. The cumulative distribution function can simply be written as f of x. And when you're looking for the actual value, it becomes the probability of x being less than or equal to the numerical value you are looking at. Now, if the alpha is an integer, then this cumulative distribution function will use something known as the Elan form. The Elan form. Now, what is that Elan form? Okay, so the Elan form is written as this. This is what we are going to use to be able to represent not a probability distribution function, but a cumulative distribution function. Take note. For some of the terms you will know. For example, what is the E? What is the E?
Exponential.
Yes. Okay, the exponent of the natural log. Okay.
Yeah.
Now, this Elan distribution, it was developed by a certain man known as A.K. Elan. And the idea of the Elan distribution is to examine, in fact, what they were doing was to examine the number of telephone calls that might be made at the same time. So let's say you are making a telephone call in your house. I'm making my telephone call. Okay, we are all making the same telephone call at the same time to the operator of the switching station or something like that. Okay, and therefore it will have a true parameter family of continuous probability distributions, which we have been talking about. One will be the shape and the other will be the rate. The shape is alpha here. The rate is the beta there. Now, the Z is the standardized formula that we are going to use. We'll talk about it. And then, of course, the Z is given by the random variable divided by the rate. Okay, so the Z is X over beta. And that's the same Z that will be here. And then the M is that particular, remember, it's cumulative. So if it is cumulative, you start from 0, 1, 2, 3, all the way up to alpha minus 1. So if alpha is 6, then the alpha minus 1 is going to be 5. And so you have to calculate the cumulative density function from 0 to 5. That is what it means. And that will give you the cumulative density function for a gamma distributed random variable. Okay. So this is a formula, just as you had a binomial formula to be, something factorial divided by something x factorial into bracket n minus x factorial, all raised to the power, blah, 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 blah. The same thing that you can have here for the gamma. Now let's examine a little bit about the function and the distribution and the cumulative density function. I told you the cumulative density function is represented by f of x. The probability, let me go back here, then you see. The probability density function, the f of x, this small f of x is a probability density function because you are looking at 1. But the cumulative is capital F. So take note, the cumulative is capital F, and then the individual, that is not cumulative, but the probability density function is small f. Now, the cumulative density function does not admit a closed form using elementary functions. And you will see that as we go, it doesn't use a closed form, it uses an expanded form, okay? And you must have an upper limit and a lower limit. For the standard gamma distribution, where beta was equal to 1, which we spoke about, the cumulative density function can be found using a table, okay? But I will not be bothering you guys to be using the gamma table. There's a way we work it out, so no problem. So if you take this particular random variable, x, which is gamma distributed with an alpha beta shape rate, then watch this. Then the x over the beta. Now this x over the beta reminds you of the z. Do you remember? Write some of these things down while I'm talking. So the z is the x over beta. That is here. Okay, it's the same thing that you have here. Okay. The x over beta. That x over beta is also said to be distributed, gamma distributed with an alpha and 1. So use this result to be able to establish that the probability of the gamma distribution with any scale parameter, okay, which is alpha, can be obtained by again referring to the table for the standard gamma distribution with a scale of 1. Again, I'm not going to bore you to use the table, but this is what you got to know. There's a trick in finding the table. So let's say that you have an alpha value that is 5 and a beta value that is 1. The alpha value reduces to 4, beta reduces to 9. Alpha reduces to 3, beta reduces to 8. Alpha increases to 6, beta increases to 1.3. What do you see the trend, the pattern of the gamma distribution here? With this different probability plot, what do you see happening? What do you see as alpha and beta rise? What happens to the distribution?
It looks more normally distributed.
I can't hear.
It looks more normally distributed.
Exactly. So what does that tell you? That we can approximate a gamma distributed probability density function to a normal distributed function when what happens? When you do what?
Doc, when you increase the alpha and beta.
That's it. But how do you increase the alpha and beta? That's the essence of our discussion here. And by the way, you can see that the thing is moving towards a normal distribution from the blue to the sort of green line. Let's take an example to see how we compute, and first of all, how do we even identify that this thing is exhibiting binomial distribution or Poisson distribution or negative exponential distribution or gamma? There are some keywords that you will see. So let's look at this together. Suppose the survival time, and the survival time here is a random variable. Suppose the survival time, X, which is in weeks, of a randomly selected male mouse. Okay, we normally use this male mouse in clinical experiment. Suppose the survival time, X, of a randomly selected male mouse. The mouse has been exposed to 240 rads of gamma radiation. So clearly it tells you that this is a gamma distributed situation. And that exposure follows a gamma distribution with an alpha of 8 and a beta of 15. Question: what is the probability that if I pick a mouse at random, given this above scenario, that mouse survives between 60 and 120 weeks? That mouse will still survive. So there's one thing you take note to know that this is a gamma distributed. It has to do with survival time. It has to do with the ability for something to sort of come to an end. Are you guys with me?
Yes, Doc.
The possibility or the ability of something to come to an end. Because remember, gamma distribution is a continuous distribution, and it is used for waiting times. Waiting time. So it means that anytime you are waiting for something, it will get to a point where the wait will be over. In fact, when we come to this topic known as queuing model, okay, we will talk about this kind of distribution, because that's why Q stands for wait. If I say go and queue, I mean go and wait. So it carries the idea of survival time. But in this question, it was so obvious that you were even told that it is gamma distributed. So, and that whole thing itself is a gamma radiation that was given to the mouse. So clearly, this exhibits gamma radiation. Now you're being asked that if I pick a particular mouse at random, what is the probability that that mouse is going to survive between 60 to 120 weeks? Given the fact is that the survival time X, is when the animal is exposed from 240 rads of gamma radiation. So how do you go about it? The first thing to do is to note the formula for the probability density function. This is a formula for the probability density function. You want to write it down. Even though some of these formulae you'll be given, still write it down. This is the probability density function, but it's not a cumulative density function. Every element you know about it. This is the gamma, capital gamma, okay, which is actually the gamma function. This is a beta raised to the power alpha. That is a rate raised to the power the shape. This is the random variable raised to the power the shape minus 1. The exponent of negative of the random variable divided by the rate, and the random variable must be a positive number. Of course, it can be a positive continuous number. Okay. The next one, I'm sure you finished writing it, is a cumulative density function. This was the one I told you to write before. If you've already written, then we don't need to write. I'm sure you all have it. But this is a cumulative density function, which has the same thing. The only thing is that you have capital F. And watch how it is. You take 1 minus e raised to the power negative z. Of course, that z you know is x over beta. And then you have alpha minus. So you have to identify these elements from within the question. So What is alpha? From within the question, what is alpha?
Doc, alpha is 8.
What is beta?
Beta is 15.
Okay. So alpha is a shape, beta is a rate, and then you can find a relationship for the scale, okay, during the scaling process, because remember, we'll be doing scale. So you can have something like 1 over the beta, and this is called the scale. Okay, we don't normally write it, but this is it. Let me see if I can show you. So you have the gamma distributed, the x distributed as gamma, the shape is 8, and then the rate is 15. The scale can be represented by theta, which is just the reciprocal of the shape. Okay. Now, if you multiply, so if I cross multiply this one, you see that the beta will come to the left-hand side, the theta will go down, okay, and that actually is the what? Is the shape. Sorry, that actually is a rate. Okay. So if this beta here, sorry, this theta here, if I replace 15 here, it's going to be 1 over 15. But if I cross multiply, okay, it means that whatever the theta is should be able to help me to be able to know the value of beta to be 15. What do you think will be the value of theta for me to get the 15 as a beta? It's 0 point something, isn't it?
Yeah.
So I need to divide 1 by something to be able to get that value. Jerry, are you here?
Yes. Yes, Doc, I'm here. Doc, I'm here.
Okay. All right. Very good. So we are now ready to find the probability. Watch the sentence, because anytime you have to find probability, you get a question on this in exam too. Anytime you have to find probability, take note of the 60, take note of the 120. They are the x variables. I always tell you that the x is the one that defines what you are finding. Okay, so they are the x variables. So first thing you got to do is to write that function and also convert it to cumulative, because watch it. Okay, it says that between. So between means that we are looking at the cumulative of 60 to 120, which means that if I want to find it, and watch it, if I say that you are moving from 60 to 120, okay, or 60 to 120, the cumulative value means that I need to find this 120. I need to move straight, because it's a continuous value, to 120, and then subtract the 60 from it. And that will give me from 60 to 120. Do you agree with that?
Yes, Doc.
Good. So that's the principle we're about to use here. So first thing we are going to do is that we're going to write the random variable in a form of a range like this. So that I'm finding the probability that this gamma distributed random variable falls between 60 and 120. That means I need to find the cumulative, that's why you have F, the cumulative of 120, and subtract the cumulative of 60 from it. Okay. So how do you find that cumulative of 120? Well, just take the 120 value. Okay, you were given that value. Okay. And remember, what we are doing here, that these are x variables. So we are going to standardize it. Do you remember the standardization formula? The standardization formula is given by x divided by beta. So for each of them, for the 120 and for the 60, find the x over beta. Let me know when you find it.
Okay. Doc, for the 60 is 4.
Mm-hmm. So that will be the lower
And then
bound.
for the,
It is 8.
yeah, for the 120 is 8.
Very good. So you now find the value of 60 and then the gamma value for 60 and gamma value for that. And this is going to give you the answers that you just spoke about. Now, once you are done with that, you have to use the Elan formula. You remember that Elan formula we spoke about? Let me go back here to remind you. You are going to use this Elan formula because we are talking about cumulative density function. We're going to use this Elan formula for cumulative density function for gamma, and then we substitute the values and then find that. So let's see, how do you work that? So first, you write the formula. So the Elan formula we are going to use, and then we calculate the finite sums. Because remember, the formula has a summation of certain things. And that certain things is from 0 to the upper value of alpha minus 1. Okay. So this is it. So if you can remember, the formula is 1 minus e raised to the power z, and then alpha minus 1. Alpha, I've just put it there directly because we know the value of is alpha 8?
Yes.
Okay.
Yes,
Okay.
Doc.
Very good. So that's 8 minus 1. So it starts from all the way from 0 to 7. That's what alpha is going to be. And then you have z raised to the power m. The m is be each one that you are finding at that point, each of those cumulative values. So if I'm doing for 0, m will be 0. If I'm doing for 1, m will be 1. If I'm doing for 2, m will be 2. Okay, and then do the calculation. So let's try 1. So let's compute for this one. Okay, remember the sum is 7 at the top, 0 at the down. So let's calculate for z equals to 4. Because remember, you got to know the value of z. Remember that we had 60 for the z equals to 4, isn't it?
Yes.
The random value for 60 is z equals to 4. And the random value for 120 is z equals to 8. We are going to do for z equals to 4. So wherever we see z here, we'll put 4 there. Okay. Then we will now calculate the terms, okay, from 0 to 7. So you're going to put 0 here. Wherever we see m, you're going to put 0 there. So first of all, you're going to have 1 minus, for this one here. For this one, it's going to be 1 minus e raised to the power what?
Negative 4.
Negative 4. Okay. Then this part here, you're going to get negative 4 raised to the power what? 0.
0.
Divided by what?
That would be 4.
Very good.
No,
It can be 4.
the 4 is positive.
Which
The
one?
Z. The Z4.
Oh, sorry. I even said 4, but I'm writing negative. So it's 4 raised to the power 0 divided by 0 factorial. But remember, we are calculating this, and this summation means that we are going to add it. So I'm taking this one, forget about this one for now. I'm taking 4 raised to the power 0, 0 factorial. That would be a value of what? 1, isn't it?
Yes.
Yeah.
Yes, it's 1.
Very good. And then when you do for 1, what will you get? So 0 will be
You get 4.
You get 4.
Doc, you get 4.
And when you do for 2, what will you get?
That will be
8.
Very good. And when you do for 3, you get what? Don't worry. At least you get a principal, isn't it?
Yes.
So the 3 is going to be 10.6. Okay. And then all the way up to what number?
Doc, 7.
Exactly. Okay. So once you get a principal, I can show you the rest. So you do for 1, 0, you get 1. You do for 1, you get 4. You do for 2, you get 8. You do for 3, you get 10.6. And then you keep going on to the last one, which is 7. That'll give you 3.25, so forth. Now, once you've gotten all of these, what do you do with them?
Doc, you add.
You add them. Okay. You're going to sum them together. Okay. So here is it. Okay. I sum all of them together. And then you're going to get the value of 51.81 thereabout. So that gives you this one. What do you do with that number?
Doc, you multiply it to the 1 minus e raised to the power negative c.
Actually, you don't multiply it by the 1 minus e raised to the power z. You multiply it by what?
The e raised to the power negative z.
Exactly. So remember, you're only multiplying it by this one. And then when you finish, you subtract the whole answer from what?
1.
That's it. So I'm leaving you with this one to do it. This one I want you to, I've given you the value of 5.8. Let's all use 5.81. You need to know where your calculator is with e raised to the power negative 4. And tell me the value. And let me see.
I don't calculator.
Sorry?
My calculator.
And that's what I want you to calculate. Because if I give you, punching your calculator will help you to know where these numbers are. Let me see which one of you is finishing first.
Okay. Doc, I got 0.05.
Okay. So that is similar to that. So when you do for the z, you're going to get approximately 0.051, blah, 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 blah. Very good. Do for the 8 as well. So we did it for x equals to 60. Do for x equals to 120. And tell me the value now. Of course, when you do the calculations and you need the answer for the other one. Okay, so let me give you the answer for the cumulative density function, because that will take some time to, but at least you all know the idea of it, don't you?
Yes, Doc.
Because that one, you got to calculate in the exam. So that is 1,350.26. 1,350.26. That is a cumulative value. Just as we had for the 60 to be 51. So use that to find me the value for the cumulative 120.
Okay, Doc, I'm getting 0.547.
The rest. Benzus, are you here though?
Yes, Doc, I'm here.
I'm not hearing you. Jerry, are you here?
Doc, please, I'm here.
What have you found?
I don't have calculator, so I'm still struggling with it.
Okay. Benson, and you two don't have calculator?
No, I do. I'm doing it on my phone.
All right. So when you do it, you're going to get 0.547 thereabout. Emily, what did you get?
Doc, that's what I said, 0.547.
Very good. So this become the two numbers. What do you now do with the two numbers?
Doc, you subtract the first one from the second one.
Excellent. So you write it like this. You write it in the X format. You can write it in the Z format. But here we are even writing it in the cumulative Z format. Okay. Remember, in Z format, you're going to have it as 4 on the left side, less or equal to Z, less or equal to 8. And then you're going to have the cumulative to be the 120 minus the 60. So you take the second one from the first one, and that will give you approximately 49.4959. That becomes, so the chances that a normally distributed mouse, okay, will survive this gamma radiation, the chances that a gamma distributed mouse will survive this gamma radiation between 60 and 120 weeks, the chances are just almost 50%. Almost 50%. If you correct it to 3 decimal places, you get almost 50%. Like I said, one can also use the table to be guided, but this approach is flexible. That's it. Now, any question on that before we go to the next? Okay, the next one. Let's take another example and again, try and find out what is happening here. Suppose that the time spent by a randomly selected student who uses a terminal connected to a local time-sharing computer facility. Suppose that time spent by the student has a gamma distribution with a mean of 20 minutes and a variance of 80 minutes. What are the values of alpha and beta? Now, watch the question carefully. Okay, you have been given the mean. Do you remember I told you to write the formula for the mean?
Yes, Doc.
And you had the formula for the median. So now the question is a very simple question. What are the values of the alpha and beta? If you look at the formula, you remember that the mean has been given here and the variance has been given there. And these two are equal to the formula that you wrote. So you should do that and find out the alpha, change of subject, and then the beta. But of course, remember that one of them will contain the alpha. Both of them will contain alpha and beta, isn't it?
Yes.
So you got to know one to know the other, but there's an approach you can sense. Okay, because let me see what I can crack that. There's an approach you can sense since there's alpha in both formulae. So I want you to struggle a bit and let me see. All right. So let me just go over that again for that guy who says he doesn't have a calculator. So you solve it simultaneously. You make alpha the subject here. You get 20 over beta. You drop this alpha that you found into the variance here. So now you are going to get 20 over beta. Multiply by beta square equals to 8. You cancel. You are left with beta. You divide both sides by 20. Beta is 4. Drop 4 back into this. Okay. Into this second one here. And you have 20 divided by 4. And that gives you 5 for alpha. So when you have a mathematical mind, it doesn't matter whether you've been taught the thing or not. So that was the first part of the question. What are the values of alpha and beta? Okay. What is the probability that a student uses the terminal for at most 24 minutes? Now that you know the values of alpha and beta. Now, first of all, let's go back to the solution that we had here. So this is it. This was the alpha being 5 and then the beta being 4. So we have the element. Alpha is 5, beta, which is the scale, is 4. And you can find the rate, which is just 1 over the beta. The rate is a theta, which is 0.5. Okay. Now, what is the probability? The question says, what is the probability that a student, let me just see where I can go to that. There's a question. What's the probability that a student uses the terminal for at most 24 minutes? Now,
Doc, please, before we continue with this, what do we use the rate for? Because I don't think we used in the last question, we didn't use the rate.
You don't use the rate for, the rate talks about the rate at which you are able to swiggle between the two intervals. So, for example, the first one we did, the interval of 60 to, we said that the mouse was going to die. What's the probability that a mouse will die between 60 weeks and 120 weeks? Yeah. What is the probability? Okay. The probability that a mouse will die between 60 weeks, but what is the rate at which that probability will occur? In other words, if I were to take every other mouse, is that the same thing? Is a mouse going to die at a particular time? Or is it going to take that same period? Because we have a range of 60 to 100, 120. Let's say that a mouse dies at 100 week. Okay. The mouse dies at week 100. Please, just a second. Dr. Ferguson, I'm teaching the PhD student. Yeah, when I finish. All right. So the rate at which, so this mouse dies at week 100. What shows that the next one, the mouse will die at week 90 or that, okay, the rate. But to be honest, once you always have what do you call it? The scale, the scale. Okay, once you always have the beta, you can always find the rate. As you can see here, anytime you have the beta, it's just reciprocal of that answer. That gives you the rate. Okay. But most of the questions will not be using the rate. But here I just needed to let you know the formula for the rate. That's why I wrote the 25%.
Yes, sir.
The next thing is to now find the probability that a student uses this terminal for at most 24 minutes. The word at most is what symbol?
Less than or equal to.
So it means that we are looking for probability of X what? X is less than 24, isn't it?
Yes.
So you are looking for the probability that X is less than or equal to 24. Now, let's go back to the question. We know that, first of all, you are doing a gamma distribution, and you have the 2-parameter continuous distribution there. And you are now looking for the chances of a gammally distributed X falling below or equal to 24. And you know that there is a formula for finding that. Well, you see, it is below 24. So that is what kind of formula you are looking for. Is the Allen formulation. Do you get it? You are using the Allen, the AK Allen continuous distribution function. That is it. Because why are you using that one? You are using that one because the nature of the question, let's go back. The nature of the question, you see, the nature of the question says you are looking at most 24. So there is a kind of a range of values that you are looking for. It's just like when you did the 60 and 120. Again, that was a range. It wasn't at a point. At a point, it would be to use what formula? Not a cumulative density function, but then the probability density function. I got it.
Yes, Doc.
So we are going to use and the cumulative probability density, cumulative density function requires you to use the AK-Ln continuous, the CDF. So that's what we are going to use. And this is a formula for that. We all know the formula. We've used it some few minutes ago. Now here, I decided to, instead of the Z, I replace it with the usual number, which is X over beta. So that is one you are going to use. We are calculating for what? For 24. So how do you find it?
Yes.
Everything 24 or less. So first of all, you need to substitute. What is our alpha here?
Like the alpha is 5.
Beta.
4.
And that means that we can find our z. What is our z?
Yes. So Z will be
What is our x?
X is 24.
Good. So
So
z,
24 over 4.
which is 6.
Yes, it's 6.
Yeah, 24 over 4 is 6. So now you are going to put it into the formula. Okay. But remember that I don't know why again. Well, sometimes I use that, sometimes I use that. Do you realize that here I've used N here? The letter N for no. But the previous one, I used M.
M, yeah.
Yeah.
I used M for mango, right?
Yes.
Yes,
Yeah.
bro.
I just want to be consistent, otherwise. So, yeah, just a second. Let me be consistent there. I mean, it doesn't change anything, but when it is consistent, it helps. Let me just. Okay. So the thing wasn't moving. 1, 2, 3, 4. Okay. So, yeah, you have to use a. That is a. All of a sudden, the thing is not showing. Just a second. The thing is not showing the sliding. So, I don't know what happened, but for some reason, it's removed all my sliding, my pauses. So anyway, you can still be working. So first thing you want to do is, you know the values of that. So you plug in for 0. So just give me the value for 0, 1, 2. You know, you're going to calculate that formula. You're going to use, you're going to use the formula. Let me show you. So you are finding this. Okay. You find this. And so it means that you got to use this formula. Now the M is published.
Yes.
Sorry, there wasn't. I said it wasn't. Okay. I miss. I just missed one thing. You didn't see that. It was there. So find it for 0 and let me see.
Okay, 0 will be 1.
0 will be 1. Very good. And 2?
Block 1.
No.
1 will be 6.
Uh-huh. But I said 1, 2. So what changed?
No, you said 2. As in, do for 2. So I was asking, why not 1?
So 0 is 1 and 2 is what?
Yes.
0 is 1 and 2 is what?
Doc, 1 is 6 and 2 is 18.
Sorry. Yeah, 0 is 1, 1 is 6, 2 is 18.
Yes.
What about that? What about 3?
3 is 36.
Very good.
There's 36.
Are you guys following?
Yes,
Yes.
Doc.
Yeah,
Yes.
3 is 36. And then, what about 4? I think it ends at 4, right?
Yes, that's 54.
Yeah. That's it. So now when you add all of them, what do you get? When you add
115.
exactly, you get 115. So that's what you see here. So you're going to take this 115 and then you are now going to multiply it by this x over beta, which is the 24, which is a 6. So you're going to have this negative 6, which is what you see here. Once you multiply by that, you subtract it from 1. What will be your answer?
Mm-hmm. 0.715.
The rest, can you confirm?
Yeah, 0.7149. So rounded up. Yeah.
Very good. So that is the value that you get. Let me just show you here. So you get, substitute this, and you get 0.715 approximately. That's it. So the chances, what's the question? The chances that the student at the terminal is going to be at most 24 is just, it's quite huge. It's 71.5%. Okay. That becomes the probability that you have calculated it. Now let's go to the C part of this question. The C part says you should find the probability of, the number being between 20 and 40. But let me go to the original question, then you see. It says that what is the probability that a student spends between 20 and 40 minutes using the terminal? What is the probability that a student spends between 20 and 40? So first, you need to calculate when x is 20 and find its corresponding z, and then calculate when x is 40 and its corresponding z. And once you have this z, you now put it into the AKLN cumulative density function. Now, why should we do that? Because you have the 20 and you have the 40, so you have a range. Okay. And because you have the range, you will now do the cumulative for the 40 minus the cumulative for the 20, isn't it?
Yes.
Yes.
They tell me the answer. So go for it. Who is ready to rock and roll? Who has done the 20, first of all?
Okay,
What was the Z values for both of them?
Okay,
5 and
Doc,
10.
for 20 is 5.
And then, who was talking? Ben. What's
Yes,
the
I was
40?
saying for that one was 10. For 40 was 10. 10,
So you're finding the Z of between 5 and 10.
20. Yes. Okay. Put that one. This one is the guilty.
So what was your cumulative density function for 20? Oh,
Yeah,
that is even shown on your
it's showing,
screen.
yeah, it's there.
What about for 40?
Okay, I'm working on that one.
Is it your finite sample summation that you are struggling? It's taking long.
Yes, Doc. Let's
Oh.
judge each.
Let's move on. I mean, you can do it. That's it. That's the most important thing. You can do
Yes.
it.
Yes,
Very
Doc.
good. So when you do the 40, you get 10 for the Z.
Yes, Doc.
And then you calculate from 0 to, what was your 0 value? For the 10.
0 be 1.
And then
1.
2.
And then 1 was
1 is
10.
1 is 10 and 2 is
2. So 2 was 50.
so whatever it is, whatever answer you get summing them, you multiply it by e raised to the power negative 10. And whatever answer you get is subtracted from 1, and that will give you 0.97. You now subtract the first one from the second one. The first one is 40. The second one is 40. The first one is 20. So you subtract the cumulative of 20 from the cumulative of 40, and that will give you 0.411. So that's the most important. So on the basis of this, when you're analyzing a gamma distribution, what do you need? What are the clues? Anybody? What are the clues?
Doc, you need the alpha and beta.
You need the alpha and beta. But then, of course, they won't use the word alpha and beta. So what will give you the clue that this is alpha and beta?
Doc, they will use is it the shape and rate?
So the shape and the scale. The shape and the scale. Remember that the rate, let me just remind you some few things. Okay. The rate is the theta. That was the question you even asked about it. The rate is the theta.
Okay, the 1 over beta. Okay.
So it's the shape and the scale.
The scale. Okay.
That is. So once you have the shape and the scale, you are in it. But for most of the time, you might even see that it is a gamma distribution that you have been told to get. Once you go by that, you are fallen. That is gamma for you. Last one we want to look at today is exponential. Exponential. Exponential distribution is also for continuous probability distribution. You know, continuous means that you can have decimals, unlike necessarily the discrete that you must have a whole number. It's very practical when you're dealing with waiting times as well between independent random events. But here is a clue for that one. It deals more with the time it takes until failure happens. We've done something similar to that, if you can remember, negative exponential distribution. Sorry, negative exponential, is it?
Distribution, yeah.
Yeah. We've done something
Yeah, it's
like that.
distribution. Negative binomial distribution.
You know, the time it takes for a failure to happen for a system. And this has to be having a constant failure rate. You must have a service times in a queuing process. So you will later learn in this afternoon that, or not this afternoon, in queuing models that we shall do in the other course, that a queuing model must have the service rate and arrival rate. And while the service rate, one of them follows a negative binomial distribution. Sorry, negative exponential. One of them follows an exponential distribution. The other follows a Poisson distribution. Okay. And you're going to learn. And this is a typical, that's why I say that the services times in queuing processes. So it's used a lot in queuing models. And then the inter-arrival times for Poisson processes is also used there. Airlines use it a lot. Radio stations use it a lot. Now, so those are some of the practicalities, but let's try to understand what it involves. So to start with, the gamma distribution has a shape parameter which is equal to 1. And then the scale parameter which is equal to beta equals to 1 over lambda. Now, this very one is not usually the case, but when this is the case, when the alpha is 1 and the beta is 1 over lambda, that will reduce to exponential distribution with a rate of positive value. In other words, which one is part of the other one? Is it that the exponential is part of the gamma or the gamma is part of the exponential? Or one is a special case of the other? Which one?
Exponential should be a subset of gamma.
Exactly. The Expo is part of the gamma. So the Expo is a special case of the gamma. That's why it's not going to be too difficult. But you still have to know the probability density function. Probability density function is not that many. If you can see, it looks like it's a one part of the gamma that is used. You remember that part of the gamma that has, you know, e raised to the power negative something. That part of the
Z.
Yeah, exactly. The only thing is that because we are not dealing with a particular random variable, but then we are dealing with a rate, a parameter, which is more or less like the mean for Poisson distribution. That is why you see that this one is not just Z, it's not X over beta, but it's a lambda X. So similar to the gamma, this one, all you need is the lambda and that of the X. That's what the E, we know it already. So that's the probability density function. The most important thing for you to remember is that the X is time until failure. Okay. Unlike the gamma one, where X is, say, time. Okay. There's no limitation of until failure. So this one is asking the question of what is the probability that the system is still alive? What is the probability that the system has not failed after this number of times? That's all. That's all the exponential distribution is asking. Okay. So if X is exponentially distributed, okay, or it is an exponentially distributed random variable with a parameter lambda, which is the rate parameter, then we can say that the mean is the beta. the mean is 1 over the lambda, and the variance is 1 over the lambda squared. That is it. That is it for exponential distribution. The mean is the 1 over lambda, and the variance is 1 over lambda squared. Now, if you can remember Poisson, the mean is lambda, the variance is lambda. Now, what about a cumulative density function? Because remember the probability density function is having this formula here. Okay, and whatever you have done here, 1 minus that, if the data I'm talking about is a range, then 1 minus that is a cumulative density function, which is what you have here. So take an example. There's also something you should learn to calculate, because we are talking about the probability that the random variable is still alive. It's still, it's still alive. The probability that, the system is still alive, is not failed after a certain time. That will require us to know the survival function or the reliability, because if you are still alive after 2 years, then your survival rate was within that 2 years. So there's something you calculate called the probability the weight is more than something. Okay, and so you calculate something called the reliability function or the survival function, and this is giving us the e raised to the power lambda time. So these are 3 major formulae that you got to know of. And of course, the mean and the variance. The probability density function, the cumulative distribution function, and then the reliability or survival function. Sometimes there's a lot of talk also about the moment generating function, which is giving us this. Again, once you know your lambda and you know your time, all of these things are deductible. Moment generating function. Okay, that is because remember that the survival rate is like the time it takes for you to wait before you die off, before you fail. Okay, and then within that time you are waiting to die off, you can choose to die off later. You can split it into parts, okay, of the time it takes for you to die, or the time for you stay alive. And that is a moment generating function here. But the key aspect of the exponential distribution depends on the rate parameter, which in this case is the lambda. The more the rate parameter increases, okay, the further away you are moving, from the origin. The further away you are moving from the origin as you descend. Okay. We have already given this function, the cumulative density function. This is the same thing up here. It's 1 minus e raised to the power, blah, blah, blah. Now, there's something we want to do. We want to find the median condition. And to find the median condition for this, we use a cumulative density function. We are deriving a certain median condition. I can tell you the formula, but I'm going to show you how I derive it from the cumulative density function. So we can set the cumulative density function to 0, because median, if something probability is 1, it means that half of it is the middle, which is 0.5. So we set this whole thing to 1, okay, and create the median condition. And then after that, we take the natural log. Watch it. So we take this function here, we set it to 1, we set it to 0.5, okay, because we want to find the median. We want to find the median function or the median condition. And at this stage, you can find the x. Okay. At this stage, you can find the value of x. Or you can find a function where x is sort of on its own. Because we need the x at the point where the median, see, in short, this is what we want to find. We want to find this value. Okay. So it's like me telling you that make x being that, make x equal to the subject. So what have I done is that I have set x to be 0.5 here. And I'll drop that into this. and then I want to find the value of x being 0.5. Now, how do you find that? Well, one thing you can do, first of all, is to start moving things away, okay, from the x. So how do you move things away from the x? Well, you can subtract 1 from each side, isn't it? Here,
Yes.
you can subtract 1 from this, so that this part 1 will go, and then it's 2.5 minus 1. That will give you something like this. Okay, so you now have minus 0.5 on the right side, and then on the left side, this 1 is gone. And now you can see that you'll be left, if you kill the negatives, if you kill the negatives on the left side and negative on the right side, you'll be left with positive values here. The question is, how do we find x subscript 0.5? Well, at this stage, there's something you can do. What can you do? You can take the natural log so that you remove the exponent. Do you get that? You can take the natural log. Okay, so the natural log will kill the exponent. Then you take the natural log on the right-hand side for the 0.5. Are you guys with me? You just take the natural log on the left side, the natural log on the right side. So you have this one here. Okay, so the natural log will go, and then the right-hand side will have the natural log of 0.5. Okay, that means that at this stage, because you are looking for x, so you will find actually the natural log of 0.5. What's the natural log of 0.5? It's 2. Okay, so the natural log of 0.5 is 2. So you take the log, is it 2? Is it 2? Okay, so from here, let me draw this first. From here, you can divide both sides rather. You can divide both sides by -1 to kill the minus. You divide both sides by -1, you divide this one by -1, you have 0.5 divided by -1, giving you 2. But of course, it's negative because the top part is positive. Are you guys with me?
Yes.
Doc, please go over. Yeah, that part is not that clear.
So here, you divide this by -1, you divide this one too by -1. Okay, so this whole thing will go.
Okay.
Leaving this. And then here, you have 0.5 divided by -1, giving you -2.
But it will be -1/2.
Sorry, it will be
-1/2.
negative.
Like 1/2. If you do 0.5 divided by 1 or -1, you get half.
Yes. You get half. Oh. What am I saying? You do 0.5. 0.5. Yeah, you got 0.5. Oh. What is it? Yeah, you got 0.5, which is half.
Yeah.
So I've missed something, have I?
Yeah, I'm confused about how you got the link 2.
No, yeah, that's a link 2.
Actually, I'm not supposed to even get link 2. I'm supposed to get.
I think it should be equals to 2. 2 rather, because if you find the lane of the 0.5, that gives us 2. So the lane should no more be attached to the 2.
I see.
Please, lane, what's lane?
Lane 0.5, yeah, I'm getting -0.69.
Oh, okay.
Yeah.
I'm not supposed to get an actual value. I'm only supposed to get a function. No, it's supposed to be a function. is supposed to be a function of
Is it the lambda?
no, we are making x subscript 0.5 because we are creating a function, a condition for the median. Okay, we are creating a condition for the median. So here, if what will be multiplied, added, or whatever way you can define it with the thing is becoming a little bit complex on the front. What will be added? It's not even supposed to be divided by, because eventually the next one should be lambda, because once you have this, once you take 0.25 raised to the power, let me see. Let me just see this number. Maybe that will help. Yeah, that's it. Oh, Charlie. So what you do here is that you raise it to the power -1. Okay. If you raise this to the power -1, you are going to get 2 here. If you raise this one to the power -1,
okay, yes.
isn't it?
Yeah, you get negative there. You get 2.
You get 2. Okay. And then you, of course, you attach the negative that it has. It already has a negative. You see, this one already has a -1 in front of it.
Okay.
It already has a -1 in front of it. So when you raise this to the power -1, you get 2. Hold on a second. You get 2. And then at this stage, you can kill the negatives. Okay, this one will go, this one will go. So the
No, it was 0.5 raised to the power -1 was 2, +2. So where did the negative come from again?
if I raise all these to the power -1, okay, and I raise this one to the power -1, I get +2.
Yes.
Okay.
Or the lane is also affected, so that's what is causing the lane to be negative.
Which one? I just don't get something, but I know that I just don't get why the negative comes. I know it's there, it's supposed to be there, because whatever you do to the left-hand side, you got to do to the right-hand side. You know that. So there has to be computation of to the power -1, because when you multiply this by the exponent, what do you get? When it's simpler, when you raise it to the power -1 and you multiply it by that value, what do you get?
Okay, so let me see.
See the -1.
Yeah, it will still be negative.
Exactly. That's my point.
Yeah.
And then you apply that negative to all of them.
Okay.
That is what gave this one still negative. And then now you can kill the negatives, which now gives you this. And so you can now have the x to be 0.5, which is the median condition, being ln 2 over the lambda. The fact that you have the 0.5 means that you are setting up the median condition. You don't know the values. But once you know the value of lambda, you can find the median condition. So just keep this one in mind. It's a function that sometimes you are supposed to find, but I'm just giving you the final equation. But if I just told you that the median condition is this, it might be, well, how did you get that? You get that from the cumulative density function. Let me just clear this one. Okay, so the median condition will be that. Okay, let's take a question, one question, and that'll be it for exponential. It will bring home all the points, and then I'll give you one as an assignment, or you want it as a test. I mean, the thing is that there are options. When it is a test, you get more marks allocated to it. When it's an assignment, you get less marks. Anyway, let's look at this. Yeah, most of these questions for today, I just want you to understand. So we are solving it more together. Okay. So the first one, the time in hours between breakdowns. You see, that's the survival situation. Okay. The reliability, breakdowns. Between breakdown of machine follows an exponential distribution. So that one too, you've been given the fact that it's an exponential distribution with a mean of 4 hours. Find the rate parameter. Again, just like the gamma one, find the rate parameter. So how do you do that? Remember, you have been given a mean, isn't it? So you know the formula for the mean, don't you? Did you
Yes,
write
Doc.
Okay. What's the formula for the mean? Give it to them because they may not have written it.
1 over lambda.
Good. So use that to find the rate parameter, which is lambda. These are quick answers. So. Oh, is it that hard? 1 over lambda. Is 4 equals to 1 over lambda? I mean,
Yes.
it's
Yeah,
also-
so it will be 1 over 4.
1 over 4.
Exactly. That's what?
0.25.
0.25. Exactly. So that one is no qualms about that. The next one, which is a key, is what is the probability that the machine runs for more than 7 hours without breaking? What do you think is asking you? Runs more than 7 hours without breaking. So when you go here, what is it asking you? Are you finding the probability density function, the cumulative density function, or the survival function?
Doc, it seems the survival function
What makes you see that?
because they are asking for the time it takes before it breaks down or fails.
That's it. So you're asking for the survival function. So now let's go and down, and we are checking probability of x being greater than 6. Okay. So you're going to calculate this survival function, which is this one here, e raised to the power negative lambda t. Okay. So you are finding the probability that x is greater than what? 6. That's what we are actually finding because you use the word more than, remember.
Yes.
Yes. So we have this function. If you haven't written the survival function, note it down. And find the probability that x, remember, the time it takes is what it gave you. So the 6 is actually the t. If you go to the question, it's in the question. What is the probability that the machine runs for more than 6 hours? That's the time without breaking down. So substitute and find me the survival function. The survival function, yeah, or the reliability function, or the probability that the machine runs for more than 6 hours.
Doc is 0.22.
Yep.
0.22313.
Exactly. That's it. That's it. That's it. There's no, nothing else about it. So now let's go to the next one. What is the probability it breaks down within the first 2 hours? What is the probability that it breaks down within the first 2 hours? Within the first 2 hours. What is it asking you? Is it the probability density function, the cumulative density function, or the survival function?
Like the cumulative.
The cumulative. Do you have the formula for the cumulative?
Yes.
Good. Use it. If you don't have, let me know. Remember that it's similar to this one, but of course, this one is time. But that one, it wasn't time, it was x. Do you remember? To the power lambda x. So it's a time that changes to the x from the previous question. Remember, we are looking at less than 2. Who is cracking the first code?
I got 0.3935.
Again?
0.3935.
All right, so that's the right answer. 3935. That's it. That's it. Find the median time to break down. Do you not remember the function we had? Find the median time to break down. Okay, so find the median time to break down. At this stage, you must know the lambda. So now, how do you find the median time to break down? Remember, everything is in hours. Okay, watch it. Hours. Okay, so what would be the median time to break down? That means I need to use the median condition. The median condition is this. So the median time to break down is x 0.5, but that is lim 2 over lambda. So that becomes lim 2 over what? What is your answer?
2.7. So 2 hours, let's say about 45 minutes.
Exactly. Yeah, 2 hours. Let's say 2.5 hours. So it's 2.7726 hours, isn't it?
Yes.
Correct. That's it. All these things you are finding, these are the answers. Okay. These are the answers. The one we just found, this is it. 2.772 hours. Now we are left with the last one. The last one, I'm going to let you solve it. I'll not even talk what it is. Solve the last one and let me know. Okay. What did you get? I just don't want us to waste so much time, but you get something. So what is the first thing you got?
The first was 0.826.
Was that for
And
the
the second
three?
was
No,
that was
that's
for
7.
7.
Okay, that 3 is 0.5276.
Oh, why am I not getting that? The probability that runs between 3.
Yeah, look, we are using the cumulative, right?
Yes, but it's e raised to the power. What was the lambda? The lambda is
What?
0.25.
That was 0.25, yes.
Yeah, 0.25.
So the first one is 0.25 times 3.
Yes.
Yes.
Then you do e raised to the
Negative.
power 0.25
Yeah.
times 7.
Yes. That is 1 minus e raised to the power.
Yes.
86.
Sorry,
So the
what
final
minus?
answer is 1 minus e raised to the power lambda and then the x.
No, you can't use the cumulative. No. Watch it. It says between 3 and 5 and 7. So you have to calculate the 7. That's what we always do. You calculate the 7, you calculate the 3, then you subtract the 3 from the 7.
Okay.
Do you remember we did something like that?
Yes.
Yes.
But those ones we were using the cumulative.
So this is the other one.
Oh,
So now we don't need the 1
No.
minus.
You don't need 1 minus. That's the point I'm
Okay,
saying.
okay.
You don't need a 1 minus. But check this one. This one here. You mean the previous one we used 1 minus, eh? No,
Yeah,
that
we were
was,
using the cumulative formula for it.
that was a cumulative.
Yes.
Yeah. No, for this, you just calculate the left one, upper one. So find the first one and let me see.
The first one is 0.472.
All right. And then the second. So
0.17347.
which one do you subtract from which?
So you subtract the 7 from the 3.
All right. You mean you subtract the 0.1738 from the 0.4724.
Yes.
And that gives you that. That gives you what you have on your screen here. As long as you understand the principle, that's the most important thing.
Yes, Doc.
So this is how you handle gamma distribution and exponential distribution. I have this for you to try your hands on at home. Okay. Try and find out this question, and then we'll continue next time. We'll look more at normal distribution. We'll look at normal distribution, beta distribution, Weibull distribution.